In a previous lesson, we took a look at patterns and sequences. And for this lesson, we're going to continue with that idea, but we're going to be focusing on a very specific type of sequence, and we're also going to represent that algebraically using a very well-defined um, representation. So let's start off with back to the idea of patterns, because any work that you're going to be doing with sequences is going to be made simpler if you can identify the patterns involved. So let's start with just identifying what the next three terms might be in each of these sequences. And we'll break them apart a little bit about what we might be coming up with there. So 3, 7, 11, 15, the next three terms are going to be 19 and then 23 and then 27. Now hopefully you see where I got those from. What's happening here is to go from 3 to 7, I'm adding the number 4. And then from 7 to 11, I added 4 plus 4, and then of course 15 plus 4 gives me 19. 19 plus 4 gives me 23, and 23 plus 4 gives me 27. What I've done here, it's a slightly different representation, but I want you to recognize that what I've done here are the first differences. So these are the delta, whether you think of them as y values. If I did it as a table of values was x and y, then the first differences would be delta y. If I was doing this as a table of values with a term number and then tn is the actual value of the term, then I suppose my first differences would be delta t. So that part's really irrelevant, how I label it here. The important part is I can also do my first differences horizontally like this. And the thing I want you to remember is that the first differences tell you the slope of the discrete linear relationship. In this case, it's telling me it has a slope of 4. We'll come back around to that idea. That's going to be important to make a connection to something we're going to be talking about today. Okay, so let's take a look at this next one. So once again, right out of the gate, let's reverse it. Let's look at the first differences. So remember, first differences is always the second term minus the first term. So if we think of this as T2 and T1, it would be T2 minus T1, or from a common sense point of view, I'm subtracting 5. 4 minus 9 is negative 5. Negative 1 minus 4 is negative 5, negative 5. So if I keep subtracting 5, I end up at negative 11. Let me change that color back. Negative 11, negative 16, and negative 21. So those are my next three terms. And in this case, if I was thinking of it this way, this would tell me that the slope would be equal to negative 5. And then finally, the last one I've got here, what am I doing? Each step, it looks like I'm adding 0.25 and plus 0.25, etc. So my next term is going to be 2, then 2.25, and 2.5. Those would be my next three terms. And of course, here, this tells me that I have a slope equal to positive 0.25. So what I've done here is really very much like what I covered in the previous lesson. So let's go a little further with it. What if I started off with this sequence, but now I asked to go a lot further to find the 100th term and to find a general expression. Now we talked about general expressions in our previous lesson, but I'm still going to go through this reasoning again. The first thing we need to start with is, once again, what are the steps involved? And very importantly here is not just what are the steps, but are the steps the same? And in this case they are. I'm adding 6 each time. And so one way to think of this, again, just repeating something I've done each of the other times, one way to think of this is to think of it as the slope. Okay, so a slope of 6. And that's something we used before to find our general expression. In the previous lesson, I tied this idea of slope to the general expression. What else can we do? How about just a little bit of an application of common sense? The first term here, t1, is equal to 3, and t2 is equal to 9. But is there another way that I could think of that 9? Because we know that to go from this 3 to this 9 is to add 6. So another way I could think of this 9 is to say, well, this is the same as 3 plus 6, right? I added 6. Okay, how about going from t1, which is 3, and then we know that t2 is equal to 9, and t3 is equal to 15. So how did I go from t1 to t3? Well, if I added 6 here and I added 6 here, then in order to go from t1 to t3 directly, I had to add 2 times 6. I added 6 twice. So I could write t3 as 3 plus 2 times 6. And hopefully from there you can see that I could have written t4 equal to 3, but for t4 I had to add 6 one more time, so that's going to be plus 3 times 6. And not to get too ridiculous, so I'll do one more of these. t5 is equal to 3 plus, I need another 6, so that's going to be 4 times 6. And in general, tn is going to be equal to 3 plus, and I'm going to need n minus 1 times 6. Now this is a really long way. I'm sure that many of you could have figured this out beforehand, but I want you to see the reasoning involved, because what we've developed here, this part, this is kind of a general expression that helps us find the 100th term. T100 is equal to 3 plus 100 minus 1. Notice that I need to take one less of these steps of size 6. So if I want the 100th term, I actually only need to take 99 steps of size 6, because the first term is already taken care of. You need no steps to get to the first term. It just starts at 3. And so 99 times 6, well, 100 times 6 is 600. So 99 times 6 is 594, plus 3 is 597. Now in the original question, I did this as A and B, but I find these things very interchangeable. It depends on how you reason it out, how you think of it. And more importantly, as we go forward from here, I'm actually going to show you a generic way to write this, and I believe that's actually our next slide. And it is. So this idea of adding and adding and adding has a very special name. It's called an arithmetic sequence. The sequence is just a pattern of numbers. An arithmetic sequence is a pattern of numbers where we're going to add or subtract a single number over and over again. And that single number is known as the common difference, which we denote with the symbol D. The first term, which can be t1, or it can be f of 1 if it's the function notation, is we give that the symbol a. And so that means in general, the first term, so here's t1, let me just put that in here. There's my first term, there's my second term, there's my third term, there's my fourth term, and so on. So notice the first term is just the a value, whatever your starting constant is. The second term requires you to have one of the common differences added in. The third term requires two common differences. The fourth term requires three common differences. So notice that the number of additions or subtractions that are coming in here, the number of extra common differences, is always one less than the term number. And so that's where we get this general formula. Any term, so the nth term, starts off with the starting value a, and then we're always going to need n minus 1 additional steps of size d, or the common difference. In function notation, it looks very similar. It's just that now our value of our function, f of n, is equal to the starting value, n minus 1 times the common difference. So whenever you have an arithmetic sequence, essentially meaning wherever you have constant first differences, then you can just go straight to either of these two representations, whichever is more convenient or whichever one is asked for in the question. Now, here's a variation on that. We're still going to make use of what we just learned, but now we're going to apply it because this looks a little bit different. This one is saying how many terms are there in this particular sequence. First of all, let's just establish that this is actually an arithmetic sequence. So what are my differences? What are my first differences here? 7 minus 16, or how do I go from 16 to 7? So 7 minus 16 is negative 9. Or to go from 16 to 7, I subtract 9. 7 to negative 2, subtract 9. Negative 2 to negative 11, subtract 9. Presumably this pattern continues, and so yes, this is linear. Okay, so that means that this is an arithmetic sequence. You do not have to establish this. Okay, if I ask you a question, you just have to identify whether or not it is this type, but this is actually the easiest way to do this. Because by doing this, these constant values, which I've referred to before, I've said, well, that tells us that the slope is equal to negative 9. That is the same as the common difference. The common difference and the slope are the same thing. So now I know my d value is negative 9, and this is my a value. My starting value is simply equal to 16. So if we take those things and put them into our general equation, which says a plus n minus 1 times the common difference, instead of a, I'm going to replace that with the value 16, which is my starting value, plus n minus 1, and instead of d, I'm actually going to use the common difference, which is negative 9. So now I've got my generic term, Tn equals 16 plus, now actually you probably at this point you might rearrange this. You might write this as minus 9 times n minus 1, and that would be fine. That's the generic term. You might also expand out that bracket, 16, and then what is negative 9 times n? Well, that's just minus 9n, and negative 9 times negative 1 is plus 9, and so you end up with Tn equals 16 plus 9 is 25 minus 9n. That would be fine as well. It's up to you which one of these you want to use. If you use this one, the second one, just means you have to do a little bit more algebra to get there. I'm actually going to make use of the first one, not for any particular reason other than it would be valid for you to stop here, but be aware that there's a couple of different representations for the correct answer, and so you might get answers that don't match what a classmate has or what you see in the back of a textbook or in a solution set, so be aware that that could be the reason why. Okay, I haven't actually answered the question yet. The question wants to know about this last term of negative 245. Well, how many terms does that represent? So in other words, if this is the last term, what is the n value that goes with that term? So let's go ahead and set our last term. So I'm going to bring this down here. I'm going to set this equal to negative 245, if I could write that properly. Negative 245 equals, and I had 16 minus 9 times n minus 1. And now from here, I'm going to subtract 16 from both sides. So I end up with negative 261 equals negative 9 times n minus 1. And then I end up with divide both sides by negative 9. And I believe I'm going to end up with positive 29 on the left side and n minus 1 on the right side. And so I add 1 to both sides, and I end up with my final answer, which is that there are 30 terms in that particular sequence. I could check my answer. I could check my answer by taking n equal 30 and putting that into either of those two formulas, and I should end up with this same value, negative 245. And so if I do that, let's do this on the closer one. So I end up with t of 30 equals 25 minus 9 times 30, and that's equal to 25 minus 270, which is negative 245, which is exactly what we wanted it to be. So that's another way you could check that. Okay, and that's it for arithmetic sequences. I'm going to follow this up with the next type of sequence. I quite often will do these two lessons as a single lesson, but I thought for the videos I would break it up into two.